Welcome back everyone. This is the second video of the 12th chapter called Debugging, Troubleshooting in the program, where we can finally see an example.
Amiben végre megnézhetünk egy példát.
The first example, which we hope will highlight the criticality of debugging as a function, will be a very simple, single-line small program. For a more spectacular result, connect an LED to the microcontroller's PA0 pin, as we also did in chapters 9 and 11. Download the example codes for the chapter from the website, then upload the project code CE12_1_LED_blinking into the microcontroller.
If you want to do this step by step, and I suggest you do, because practice is very important, then rely on the curriculum that will help you with each step. However, I have already downloaded these, unzipped them, opened the Atmel Studio project, and now I'm uploading the code onto the controller.
If this is done successfully, we will see that the LED on the PA0 pin lights up. Let's just look at the uploaded code. Based on what we have learned in the software, the LED should be blinking, and as it has been discussed in the previous chapter, it is blinking as well. The processor runs the code very quickly while the LED is blinking, but so fast that the human eye is unable to detect, so we see it as constantly lit. During the introduction, it was said that optimization will not be our friend, so make sure that it is really turned off. This can be found in the project settings on the toolchain tab under the AVR/GNU-C compiler optimization section. Run the code now in debug mode. To do this, click on the Start Debugging button. We can see that the interface of Atmel Studio has changed slightly. In this mode, the code on the microcontroller runs the same way as before, but the computer keeps continuously communicating with it, so we can influence the running of the code, for example, to pause or move it line by line. Let's try the latter. In the first step, use the Break All button to stop the program from executing, then use the Step Over button to step through within the code per line function call. The functions come with key combinations, and we recommend that you use them now, so you don't have to search for them on the toolbar. The key combinations are Ctrl plus F5 for Break All and F10 for Step Over. Step by step, we can see that the LED really changes its state. So, the program works correctly, only our eyes are not fast enough to detect the blinking. The LED blinking program written in the previous chapter also worked the same way, but it contained a delay. This is necessary for our eyes to be able to sense blinking. It may be interesting to try to find out how many milliseconds delays are needed in order to be able to distinguish the individual flashes with the naked eye. Now that we are beyond the first steps, let us get to know the rest of the buttons on this toolbar, which we will use henceforth. The first three buttons affect the code run. Stop debugging. This button is used to stop debugging. It terminates the debug process and the connection between the microcontroller and our computer. It's important to stop debugging after we finish debugging and wanting to change the code. If we do not act like this, then we will not be able to upload the modified program to the microcontroller because the programmer will be busy. The next button is the Break All. When we click this button, we are suspending our program. This should be imagined as if we could stop the clock in the microcontroller. Of course, this is not the case in reality, since we would not be able to communicate with it if it was. Continue. If we stop the program from running, somehow we have to continue later. This button serves this purpose. The following buttons are also related to code execution, so we can move the code, that is, run at the pace we want. Step into. It executes the following code sequence, so that if it is a function call or a block with brackets, it enters it and executes its first line. Step over also executes the following line. If it is a function call or a block with a bracket, it does not enter, but the contents of the block are executed. Suppose that an LED is not turned on and off by simple bitwise operation, but we have a function called setLED. When you move to this function with the step over button, you only see that the LED turns on, but if you move on with step into, you get inside the function. You can then follow the steps to turn the LED on. In terms of coding, it would be more elegant to use the setLED function, as it hides the bit behaviors from the reader, and instead we call a function whose name tells its function without commenting and implements the necessary operations in the background. Other buttons on the toolbar. Step out. We can quit the function which we are currently in. The program stops at the next function call. Of course, the rest of the function will be executed, but the run will not stop until the beginning of the next function. Run to cursor. The code will be executed until the position of the cursor. Reset. It is used to restart the processor. It is practically equivalent to pull out and replug the processor's power supply, except the inconvenience that it is not needed to rebuild the debug connection. Using the remaining buttons, we can open different views to get to know the internal state of the processor. The common feature of these views is that we can not only read the different registers, but also interfere with their state, that is, we can override their values. Disassembly. If you click here, the assembly code will appear, which was compiled from our C file by the compiler. We may need this view if we want to know exactly what happens in the processor. Registers. This view allows us to monitor the contents of the CPU registers. There are 32 such 8-bit registers in this microcontroller. These are temporary containers for the data we work with. For example, if we want to add two numbers, then these two numbers are first put into two such registers, and only then can the processor add them together. If a loop is executed, then, for example, the loop counter is also stored in such a register. In the figure, they can be seen in the section framed in red. It's not to be confused with the concept of RAM, which is a memory area to be treated as a larger block. From this, the variables that are just needed are copied to the registers. Memory 1. We can see the memory map of the processor here. We can see all available memory areas in row form, encoded in hexadecimal, and even as ASCII characters at the end of the rows. Processor view. This view provides access to the contents of the registers that are closely related to the processor execution unit. These are the following: the previously mentioned program counter, stack pointer, X, Y, and Z registers, status register, and finally, the 32 general-purpose registers we have also mentioned. Input-output view. This view will be most useful to us. Here, we can examine and modify the state of all peripherals. For example, you can easily determine if something has been configured incorrectly. If port is selected, then registers that belong to the selected port will appear below. These are pin, DDR, and port. At the end, the letter A indicates which port they belong to. The pin register stores the logical value that the controller has read from the given pins. DDR means that a specific pin is configured for input and output. In the port register, we can write what value we want to see on that leg if it is configured as output. If you click on the rightmost bit of port, this is the first square on the right, then we can see how the LED can be switched on and off on the breadboard. Be patient for our configuration to become valid, as we have to wait for the programming tool to print the register contents and then read the new ones. It can also be an interesting game to test what happens if we pinch these pins with our finger and step 1 on the program. If we are lucky, we may experience some change in the value of the inputs. The reason for this is to look for the processor's electronic structure and the fact that these pins are not connected to anywhere, so they are floating. This was the second video of the 12th chapter on debugging. In this video, we reviewed the most basic features of Atmel Studio, which we will also meet in the next video. We will use them in the following example codes. Thanks for your attention. See you later.
Bye.